Welcome to Product One's YouTube web series. Today we are still focusing on Creo simulation, particularly nonlinear contact analysis. So this is all inside Creo. So if you were having a scenario where you've got two gears and you want to simulate how will these gears react when they start to meet up at a particular point. If you were to go into Creo Simulate, this is now inside Creo Parametric. We'll start with the first thing. I always make it a best practice that I assign material for all my analysis. So let's do that. So I'm going to make these steel. That's the first part. Then I'm going to simulate worst case scenario. Worst case scenario means that I'm taking that big gear and I'm applying what we call a displacement constraint. That means that that gear does not move. On the small gear, however, I'm going to assign what we call a pin connection. If you can see there, I'm freeing up what we regard as rotation, but we are constraining what we regard as translation. So simply put, I want that type of effect on that gear. So now that we've got that motion involved in that area, we need to now specify a force that will leverage that type of constraint. So I'm going to select a surface of interest, but then I'm going to do something slightly unique here. I'm going to say total loaded point. That means that the rotational axis is going to be this one. Instead of applying a force, I'm going to assign a moment. And based on the direction, I can say preview to see if the direction is right. I'm happy with that. That means that that's the direction of motion that I wanted. So that's the first part. Now, one thing to be careful of is when you're running a contact analysis, you must always remember that it's a non-linear study. So in order to get the full benefits of this, you can assign what we call contact interfaces. So that means that I know that that surface and that surface are the surfaces that are going to be in contact. And of course, you can have contact with finite friction, but we're going to do a video of that a little bit later in the series. Now that we have actually assigned contact interface at that point, I can do a couple of things. One, I can mesh or create elements of those two components, and this is the default mesh, and this is how it looks like. There's a reason why I show this mesh. I'm going to make some modification a bit later on another analysis. So that's pretty much what you need to do to define a nonlinear contact analysis. What I'm going to do here is create what we call a quick study. So if you can see there, automatically this stipulates that it's nonlinear. Instead of running an entire analysis, I'm just going to choose quick check. So due to the screen resolution, I'm just going to move this slightly here and into this other window, so I'm able to select OK in this instance because the screen resolution is small on that instance. If I run that analysis, so let's overwrite what's already there, you will see this analysis is very, very quick. So essentially, this is what is happening behind the scenes. So as it's busy calculating, you will now get a signal that the analysis is complete, as you can see there. Now I can say, show me the results of this. So the results window, here it is, and this is obviously my results dialog box. So what is it that I want to see? I want to see displacement. So I can say, show enough, show me the displacement, and this is currently what I have. All right, this is just purely displacement. It shows that there's some kind of movement here and there's some impact on this. Well, let's take this further. Why don't we say show this as deformed? We can even go as far as overlay the original gear, basically have something like this. So this is now the original position of the other gear, and this is obviously the resultant motion. As you can see, this is what you have. Of course, you don't have to stick with displacement only. You can say, show me how the von Mises stress will look like. So typically, in a scenario like this, any engineer will tell you that those are the areas that they would like to interrogate a bit further, including here. So what do you do in a scenario like that? So I can say, how about we do something like this? I'm going to close that result and I'm going to do the following. First and foremost, I'm going to apply what you call a volume region. On the previous video, I showcased what is a volume region and what is the benefit of it. So what I have here is the following. I have an area of interest which is here. This is where I'm going to get my high stresses. So I'm going to say, how about I create a circle between those two entities, let's say here. All right, and probably maybe let's just change this diameter. I'll just delete the other constraint that's there. Let's move this right into position. So let's put it probably, if we were to define this, let's put it maybe just about here. All right. So immediately when I accept that, you will realize that the volume region is only created only on one piece of geometry, because you can only create this at per component. Then we do the same thing on the other component, and for this one it's quite easy because we already have some form of reference. All that you have to do is specify now a circle, and that's pretty much it. Now that we've actually defined the volume region on all of these, this is why we're going to take what we currently have as contact interfaces. We're going to remove all those surfaces. Instead of them acting on those surfaces, we're only going to choose these small little surfaces over here. So that means that we are really honing in on where the contact is happening. So that's the first aspect. Then the other aspect will be the following. I'm going to modify the size of the elements on this. So I'm going to make this component and that component, the size of the elements to be, let's say 1 millimeter. So it's quite small. And on top of all of that, I'm going to have multiple controls at specific areas. So I'm going to say I want elements at these key regions to be even smaller. So we're talking about all these other areas. We'll come back just now onto the volume regions. So I'm not going to define them now. So I'm specifying where I've got what we call radiuses and high stresses, or in this instance. And please bear in mind, I've removed rounds and fillets in other areas where they are not going to have any impact to the results, if you can see there. So essentially, let's specify, let's make it 0.2 or 0.2. All right, so that's the size of my element. Then last but not least, let's choose volume region. Which volume regions? These ones that we just created, and we're going to make these elements way smaller. All right, so that's basically what we've got. If I were to create a mesh of this, you will see that now the mesh will take slightly longer than previously. It's still relatively quick, but it shows you that you can have multiple mesh controls, and you can also change the viewables of these as well. So for an example, the points are very much distracting. So let's have a look at how it's going to look like. And this is essentially what we currently have. You can see that the size of the elements in all those components, it's 1 millimeters. And of course here around the fillets, it's slightly smaller. Now that we're done with this, we can now start running our analysis. So in this instance, I'm going to set up a brand new analysis. Let's give it a different name. With this one, I'm going to try and give it, let's say it's a multi-pass study. And I'm going to say maybe that I'm going to leave the convergence percentage to be that. Yet again, I will transfer this to the other screen as I select OK at the bottom. All right. So now here's what we are going to be doing. So we've already stipulated that this is a nonlinear study, right? It's a nonlinear study. We can give it a different name there. Let's call it Bob. All right, so that's the Bob analysis. Once I'm done with this, I can now run it. I will just speed up the video just a bit because this analysis takes a good 3 minutes. Now that we've got the analysis complete, we can now explore the results. So just like previously, I'm going to drag the results onto this window. However, with the results this time around, we'll just move right straight into our von Mises stress. And this is exactly what we wanted to see. At a point of impact, that has been sort of like focused with smaller elements. Of course, you can modify how the results look. We can say continuous tone. We can even overlay the previous analysis or previous position if we like, but this is what we were looking for. Now, what we've done is create a contact analysis when you've got two objects in contact with one having a particular force, transferring it into another object. So for what is worth, you can also modify this and showcase the element size if maybe you want to see that on your results as well. All right, so that's the power of Creo Simulate. It's extremely easy, but very powerful. Until next time, goodbye.